Welcome to the 747-400 flight deck. Today we're going to introduce you to the Auxiliary Power Unit Maintenance page on ICAS. We'll cover some of the information that's available to assist you in doing your job. The APU is a small gas turbine that provides pneumatic and electrical power to the airplane during ground operations. Remember, before applying power to the airplane, consult the Boeing maintenance manual and go through the safety checklist. Control for the APU is provided by the APU controller, and system indication is shown on the ICAS maintenance page. To call up the maintenance page from the Central Maintenance Computer, or CMC, first, select the maintenance page from the Control Display Unit. Then, select 49 for APU, and finally, Display from the Page Control Unit. This is the information available on the maintenance page. On the left side of the screen is key APU discrete signal data, and on the right, numerical APU parameters. To start the APU, the battery switch must be on. Then, rotate the master control switch to start, and then release it. That action caused the following to happen. The APU controller is powered, and indications show on the maintenance page. The controller commands the air inlet door to open, then turns on the APU primary fuel solenoid and sets the inlet guide vanes to 47%. At this point, the controller is waiting for the APU air inlet door to open. When the inlet door is open, the controller turns on the starter and the igniters. Then it sets the fuel metering unit to 24 for starting, and it blanks the DC amps indication. At 8% N2, the controller turns on the secondary fuel solenoid, supplying fuel for combustion. This is followed by a rise in EGT, indicating APU light off. Oil pressure goes from low to normal. At 40% N2, the starter and igniters are turned off. The DC amp indication returns and shows that it is in a charge mode. At 55% N2, the inlet guide vanes are set to minimum. The APU starts indication is advanced by 1, and the run timer starts. 2 seconds after N1 passes 95%, pneumatic available and electric available comes on. This has all happened in the span of about 30 seconds. We've slowed things down so you can get an idea of the type of information that's available. Let's take a look at a real-time start. Now that the APU is up and running, we can bring the electrical generators online. First one, then two. The indications are a percent of 250 amps. The same indications are shown on the Chapter 24 Electrical Power Maintenance page. Pneumatic power is also supplied by the APU. When pneumatic power is available and the isolation valve is closed, the indications will be bleed valve closed. Operational mode minimum. Opening the isolation valve, the bleed valve changes to open, and operational mode indicates DPZ for duct pressurization. When selecting any air-driven pump, ADP shows. When selecting any one of the 3 air conditioning packs, ECS1 shows, then 2, and 3 as the packs are added. Switching on any of the main engine start switches will show MES, along with an increase in duct pressurization. Well, that's startup, and some of the normal indications that are available on the APU maintenance page. Shutdown is next. Turning the APU switch off starts an automatic sequence in the APU controller. This sheds all pneumatic and electrical loads, and it starts a 60-second cooldown timer. After 50 seconds, the controller commands the APU to spool down to 67%. At 60 seconds, the APU controller performs one of 4 shutdown tests. As the system responds to the selected test, the controller turns off one of the fuel solenoids. In this case, the secondary was shut off first. 156 seconds after turning the switch off, power is removed from the controller. Then, the data on the maintenance page blanks. Well, that's the APU maintenance page, and just some of the information that's available to you. I hope this brief introduction will help you understand the expanded APU maintenance page.
This program gives an overview of the fuel system for the Boeing 747-400 and shows the major components in that system. It covers the following subsystems that make up the fuel system: fuel storage, fuel control, fuel indication, fueling, engine feed, fuel transfer, fuel jettison, and defueling. Fuel is stored in large tanks within the wings. They are identified as number 1 and 2 main tanks, number 3 and 4 main tanks. Outboard of the number 1 main tank is the number 2 reserve tank and surge tank. Outboard of the number 4 main tank is the number 3 reserve tank and surge tank. Fuel is also stored in the center wing tank and in the optional horizontal stabilizer tank, or HST, and surge tank. The total fuel capacity is more than 383,000 pounds, or 57,000 U.S. gallons. Many of the fuel system components are located in the tanks. Access to these components is through one of the 28 panels in each wing. To gain entry to the center tank, remove the wing to body fairing, and then remove the tank access panel. A panel in the front spar of the horizontal stabilizer allows entry to that tank. When entering a fuel tank, always consult Chapter 28, Section 11 of the Boeing Maintenance Manual for warnings, cautions, and procedures. No one should be allowed entry to a fuel tank without being monitored by safety personnel outside the tank. Surge tanks are located in the tip of each wing and in the right tip of the horizontal stabilizer. Air and excess fuel are vented to the surge tank by vent tubes or hat-shaped stringers, which are attached to the upper wing structure. Fuel returns to the inboard main tanks and the air vents overboard. All tanks have sump valves mounted in the lower surface. They are used to drain water and fuel from the tanks. Sump valves in the horizontal stabilizer tank are controlled electrically from the P211 panel just inside the access hatch. Fuel drains through an exit tube in the lower surface of the fuselage. In review, the fuel storage subsystem contains the fuel storage tanks, fuel surge tanks, fuel vent lines, and the fuel sump valves. We have covered their operation and location. The 747-400 fuel system has many automated features. The design reduces the workload of the flight and ground crews. Components used for fuel system control are in 5 major areas of the airplane. Let's look at these areas and discuss the control provided by each of these components. Control panels on the flight deck provide operational management of the fuel system. The fuel management panel supplies direct or arming control of the cross-feed valves, boost pumps, HST transfer pumps, and override jettison pumps. Lights and flow bars on the fuel management panel are used to show system status and configuration. A fuel transfer switch allows manual control of the fuel transfer valves which connect the outboard and inboard main fuel tanks. The fuel jettison panel controls the automated jettison sequence. The defuel panel controls the reserve tank transfer valves during defueling. In the main equipment center, on the forward left side, is the fuel system card file. This card file contains fuel system management cards, fuel jettison control cards, valve position logic cards, fuel system ICAS interface cards, and the single point sensor cards, which monitor fuel levels in the inboard main and center tanks. In the center fuselage equipment center is the fuel quantity indicating system processor, or FQIS processor. In the aft equipment center, the remote electronics unit. It supplies fuel quantity information to the FQIS processor. Mounted in the leading edge of the left wing is the fueling control panel. It controls the fueling process and provides fuel quantity indication. In review, flight deck switches, system control cards, system electronic units, and the fueling control panel provides fuel system control. The processor in the fuel quantity indicating system, or FQIS, computes the quantity of fuel contained in each tank. The remote electronics unit, or REU, does the same calculations for the horizontal stabilizer tank and sends the information to the FQIS processor. To compute the tank quantities, the FQIS processor and REU use inputs from three components in each fuel tank. They are tank units, compensators, and densitometers. Tank units are mounted in each tank. They measure a capacitance that varies with the fuel level and dielectric constant. Compensators are mounted in the lowest point of each tank and are used to determine the fuel dielectric constant. The FQIS processor uses this information to calculate fuel on board. A non-radioactive sonic densitometer is mounted in every tank except the number 2 and 3 reserve tanks. Densitometers are mounted at the lowest points in each tank. They measure the fuel density. The FQIS processor calculates fuel weight using fuel density and volume. Mounted through the rear spar in the number 1 main tank is the fuel temperature bulb. It supplies an input to the fuel system ICAS interface card. Total fuel quantity and temperature shows on the main ICAS primary format. Total fuel quantity can be shown in pounds or kilograms. Fuel system configuration and individual tank quantities show on the auxiliary ICAS fuel synoptic display. The fuel system ICAS maintenance pages show specific maintenance information for each tank, such as quantity, density, probe capacitance, and volumetric top-off settings. This information shows for one pair of fuel tanks at a time. Fuel levels can be determined by using the fuel measuring sticks. They are located in lower skin access panels of the wing and horizontal stabilizer. Tables convert these readings to total fuel on board. Fuel pressure switches are used throughout the fuel system to monitor discharge pressure of the fuel pumps. These switches operate from 4 to 7 psi. They have the same part number and are line replaceable. We have seen the operation of the fuel quantity indication system. We have covered the inputting, processing, and displaying of fuel system information. We have also covered fuel measuring sticks used to manually calculate fuel quantity. There are two methods of fueling the airplane: over-wing fueling and pressure fueling. Over-wing fueling is only used when pressure fueling equipment is not available. There are over-wing fill ports for the number 1, 2, 3, and 4 main tanks. Pressure fueling receptacles are located in both the right and left wings. They are controlled from the fueling control panel located next to the fueling receptacles in the left wing. Opening the fueling control panel door automatically supplies electrical power to the panel through the ground handling bus. If external or APU power is not available, switching the guarded power switch to battery supplies battery power. To fuel the horizontal stabilizer tank, or HST, the guarded HST isolation valve control switch has to be in the open position. This opens the isolation valves in the center tank and the HST. Automatic fueling can be done to fuel all aircraft tanks or just the center tank to a pre-selected level. This is done by using the pre-select fueling controls. A desired fuel load is selected using the select quantity switches. The value is loaded into memory by positioning the set quantity switch to either total or center as required. The tank refuel valves can then be opened by using the all valve switch or the individual tank valve position control switches. If during fueling an overfill situation occurs, the float switches in the surge tanks stop fueling and turn the panel overfill light on. Once the surge tanks have drained, pushing the overfill reset switch will allow fueling to continue. A test panel allows testing of the indicators and subsystems. In review, we have covered the two types of fueling, the overwing and the pressure fill methods. When fueling automatically, use either the desired total or center tank selected value. Fuel is supplied to the engines from the center and wing tanks. Valves and pumps direct the fuel from the tanks through the cross-feed manifold to the engines. There are two boost pumps in each of the main tanks. The boost pumps for the outboard main tanks are mounted in dry wells in the inboard main tanks. The boost pumps for the inboard main tanks are mounted through the front and rear wing spars. The boost pumps deliver pressurized fuel from the main tanks to the cross-feed manifold. Two override jettison pumps are in the center wing tank and in main tanks 2 and 3. They are mounted through the wing rear spar and supply high-pressure fuel to the cross-feed manifold. 4 cross-feed valves are mounted in the cross-feed manifold and control the flow of fuel from the tanks to the engines. 4 fuel shutoff valves, commonly called spar valves, are mounted through the front spar. They control the flow of fuel to each engine. Flight deck control of the fuel feed components is through the fuel management panel on the P5 overhead. It has 8 switches to control the fuel boost pumps. 2 switches for the center wing tank override jettison pumps, 2 switches for the HST transfer pumps, 4 switches for the inboard main tank override jettison pumps, and 4 switches for the cross-feed valves. In review, engine fuel feed and control is supplied by boost pumps, override jettison pumps, cross-feed valves, fuel shutoff valves, and flight deck switches. Fuel in the reserve tanks and horizontal stabilizer tank transfers to the center wing or main tanks for use by the engines. Fuel from the horizontal stabilizer is transferred to the center wing tank when the level in that tank drops to about 12,000 gallons. At that point, a signal from the fuel system management card opens the isolation valves and starts the 2 transfer pumps in the front spar. Fuel pumped through a shrouded transfer line enters the center tank, then splits into 2 redundant lines, each containing an isolation valve, a primary refueling valve, and a secondary refueling valve. Fuel in the number 2 and 3 reserve tanks transfers by gravity to the inboard main tanks. It passes through the 2 reserve transfer valves for each reserve tank. The auxiliary power unit, or APU, uses fuel from the airplane fuel system for operation. Fuel is automatically supplied to the APU from the number 2 main tank. During APU operation with no AC power available, the APU DC fuel boost pump automatically supplies fuel. When AC power is available, the number 2 main tank aft boost pump automatically supplies fuel for APU operation. The APU fuel boost pump control pressure switch automatically shuts off the DC pump. The following APU fuel supply components are located on the rear spar of the number 2 main tank. The APU DC fuel boost pump, the APU fuel boost pump control pressure switch, the APU fuel shutoff valve, and the number 2 main tank aft boost pump. In review, fuel is automatically transferred from the reserve tanks and the HST. Reserve fuel flows through the valves to the inboard main tanks, and HST fuel is pumped to the center wing tank. A fuel jettison system can dump fuel overboard to rapidly reduce weight during an in-flight emergency. The fueling and jettison manifold inside the tanks runs along the rear spar. It carries fuel out to the jettison nozzles. Fuel from the override jettison pumps enters the fueling and jettison manifold through the jettison transfer valves. There are 2 jettison transfer valves in the center wing tank and 1 each in the number 2 and 3 main tanks. During jettison, fuel from the HST is transferred directly to the fueling and jettison manifold. When fuel in the inboard main tanks is jettisoned down to a specific level, the main and reserve tank transfer valves open, and fuel in the reserve and outboard main tanks transfers by gravity to the inboard main tanks. Controls on the flight deck for fuel jettison are on the overhead control panel. The fuel jettison control selector arms the system and selects either fuel jettison control card A or B. The fuel to remain selector sets the amount of fuel to remain after jettison. The value set by the fuel to remain selector is viewed on the main ICAS display. 2 guarded fuel jettison nozzle valve switches open the valves and start the jettison sequence. Caution: the nozzle valve switches are wired directly to the valves, and when selected will open the valves anytime the airplane is powered. When the jettison system control selector is moved to the A or B position, the fuel system synaptic changes to show the jettison fuel flow and the time required to jettison to the selected level. In review, the fuel jettison system allows fuel to be dumped overboard during an emergency. This is done by a series of pumps and valves that transfer fuel to jettison nozzles in each wingtip. At times, it may be necessary to defuel the airplane or an individual tank to perform maintenance. This is done by using controls in the flight deck and at the fueling control panel. Defueling begins by repositioning the defueling tab in the fueling receptacle. The defueling tab unseats the check valve in the receptacle so fuel can be pumped overboard. Then open the manual defueling valve. It connects the fueling manifold with the cross-feed manifold. Depending on the position of the tab, fuel can be directed overboard or from tank to tank when the manual shutoff valve is open. Fuel can then be pumped out of the main tanks or the center wing tank by opening the cross-feed valves and turning on the fuel boost pumps or override jettison pumps. The HST can be defueled by turning on the transfer pump switches and opening the HST isolation valves using the fueling panel switch. The boost pumps will remove most of the fuel from the tanks. To remove all of the fuel, the sump drains must be opened to remove residual fuel. In review, defueling of the airplane can be done at the fueling control panel by opening the manual defueling valve and then repositioning the defueling tab. This allows fuel to be removed from the tanks or diverted to another tank. This completes this program on the 747-400 fuel system. We have covered fuel storage, fuel control, fuel indication, fueling, engine feed, fuel transfer, fuel jettison, and defueling.